One of the fastest speedrun categories for Super Mario World, called 11 Exit, since you clear 11 levels before reaching Bowser's Castle, uses a peculiar glitch in order to speed up the fight with Bowser. You go out of your way to collect a glitch item in the first level of the game and keep it with you until the very end of the run. Because of this, you must forego collecting a fire flower in the castle of the first world, and must not get hit at all once you collect the cape feather, or else the item will automatically release from the item box. This prevents you from intentionally taking damage to take a faster path in Bowser's Castle. But all of these sacrifices are worth it, since keeping this item can shave over a minute off of the run, which is way more than what is lost from the previous things combined. Let's talk about Lakitu's Cloud, how it is obtained, how it is used, and ultimately why it is crucial to the Super Mario World 11 Exit speedrun. Part 1. Eating a football player. Obtaining the cloud is fortunately possible in the very first level of the speedrun, Yoshi's Island 2. There's a Yoshi right here, which is necessary to pull off the item swap glitch. The item swap allows Yoshi to swallow this Charge and Chuck enemy. Normally, Yoshi's tongue passes right through these guys, but with this glitch, you can actually latch him onto the tongue and swallow him. Now, I've already made a video from a few years ago that explains the item swap, but I'd like to go into much more detail in this video. More specifically, I'd like to go into more detail about what happens after a more generic item swap. If you'd like to know more about how exactly Yoshi can go from eating a coin to eating the Chuck, and why the Chuck warps to Yoshi's tongue, you'll need to watch that video. But this video will go more in depth about what happens when Yoshi eats enemies, and what is possible when Yoshi is given the ability to swallow basically anything. Most of the time, when Yoshi eats one of the variations of the Charge and Chuck enemy, the game crashes. But under certain circumstances, it doesn't, and we can get an unintended sprite in our item box as a result. That's what we'll figure out how to do in this video. But first, let's talk about power-ups. What is a power-up? I think it's easy to answer that question. The Super Mushroom, Fire Flower, and Cape Feather, of course. Is the Starman a power-up? You could argue against it, but I think so. Is the 1-Up a power-up? I don't think that counts, but according to the game, it is. Same with these moving coins that enemies turn into when you burn them with a fireball. Okay, clearly we need a better definition of what a power-up is instead of just going by intuition. Technically speaking, a power-up is a sprite in the game that will call a certain routine in the game's code that has the purpose of altering the game's state in a positive way after Mario touches or Yoshi eats said sprite. I know that's pretty vague, but let me explain. This routine, which I'll refer to as check power-up, is located at ROM address hex 01C4CB in the Japanese release of the game. There are two ways it can be called, either by touching a power-up with Mario or by swallowing a power-up with Yoshi. These are the sprites that can call check power-up by having Mario touch them: the Super Mushroom, Fire Flower, Cape Feather, Starman, 1-Up Mushroom, Moving Coin, and Roulette Item. And these are the sprites that can call check power-up by having Yoshi eat them. All of the previous sprites just mentioned, along with the bubble with a mushroom in it, touching it with Mario just pops the bubble instead of giving a power-up instantly. The invisible solid block found in Switch Palaces, 8 of the Charge and Chuck varieties, and the spotlight found in the last room of Bowser's Castle. So why are these considered power-ups? Yoshi can't even eat them. Well, there isn't really a good answer for that, other than maybe the developers accidentally kept them that way. See, every sprite in the game has a bunch of properties associated with it that determines how it acts in the game. These include all sprites, not just enemies, so moving platforms, hazards, etc. Some of these properties include things like, can Mario spin jump on it to kill it? Can it be killed with a fireball? Will it despawn when it leaves the side of the screen or stay in memory? And so on. A few of these properties are, can it be attached to Yoshi's tongue? Does it give a power-up when eaten by Yoshi? And can Yoshi swallow it, or will it stay in his mouth? The invisible solid block, charge and chucks, and the spotlight sprites all have the property that they specifically cannot be attached to Yoshi's tongue. So in theory, the other two properties, whether Yoshi will swallow the sprite and whether it will give a power-up, are completely irrelevant. You can't swallow a sprite if it won't even attach to Yoshi's tongue in the first place. Well, that's where the item swap glitch comes in. It allows any sprite to become attached to Yoshi's tongue regardless of this flag. Now, the spotlight sprite also has the property that it will stay in Yoshi's mouth instead of being swallowed, so that one still can't give a power-up anyway. Waiting for Yoshi to swallow it after several seconds never gives a power-up, only a single coin. That's too bad. However, the invisible solid block and charge and chucks are instantly swallowable and have the power-up property. So when you get Yoshi to eat them with the item swap glitch, they will indeed be treated as power-ups. It's also worth pointing out here that the roulette block and the bubble sprites are special cases here. For the bubble, if it detects that it is about to be eaten by Yoshi, it will actually transmute itself into a normal mushroom by changing its sprite ID right before running the check power-up code, so it is just treated as a normal mushroom. And the roulette block will transmute itself into whatever sprite it currently looks like before running the code, for both cases of Mario touching it or Yoshi eating it. This means that when it comes to the check power-up routine, it will be run with 15 different sprites. The 6 intended power-ups, the invisible solid block, and the 8 charge and chuck types. Before looking at the check power-up code, let's get to know these sprites a bit better. Like I mentioned earlier, each sprite has an ID number that determines what kind of sprite it is. For example, the super mushroom has ID hex 74. That's what it means to be a super mushroom, being a sprite with ID hex 74. The fire flower, starman, and cape feather have IDs hex 75, 76, and 77 respectively. The roulette item actually has ID hex 81, but it changes its ID to one of these 4 other IDs as it's being collected, so it behaves exactly like those for the purposes of being a power-up. The one-up mushroom has ID hex 78, and the moving coin has ID hex 21. The invisible solid block has ID hex 6D, and the 8 chucks have IDs hex 91 through 98. The charge and chuck with ID hex 96 is just a copy of the normal hex 91 chuck, and is not found in any level in the game. There's also a dig and chuck variant with ID hex 46, but these are the only chuck to not have the power-up flag set for whatever reason. Now these are all of the sprites' IDs, but sprites in the item box are given a different identifier. The mushroom, flower, star, and feather were the only sprites intended to be in the item box, so they were given the item box numbers 1, 2, 3, and 4. 0 meaning that the item box is empty. This item box number is just the sprite's ID minus hex 73, wrapping around at 0 back up to hex FF. So for example, the 1-up would have item box number 5, and the moving coin would be hex AE, hex 21 plus 100 minus 73. That's not really important to know for these sprites, but it is important to know that the item box number differs from a sprite's ID by hex 73. Now let's look at that check power-up routine. There are a few tables that are used in this routine that are indexed via the X register. X will hold the slot number that the power-up sprite is in. Super Mario World only has memory allocated for 12 sprites at a time, so X just lets us know which slot we're working with here. The first thing that a power-up does when it is collected is checking if a certain timer is greater or less than 24. This is a timer that is used as a power-up is coming out of a question block, so that Mario can't collect it right away. It has to come about halfway out of the block before it can be collected. When this check fails when Mario touches the power-up, it sticks around for the next frame where it is checked again. Eventually, the power-up will be poking up out of the block far enough and Mario can collect it. However, if this check fails when Yoshi eats the power-up, Mario doesn't collect the power-up, but Yoshi still swallows it and removes it from existence. This essentially deletes the power-up without actually collecting it. Yoshi is being just a bit greedy there. If this timer check passes, then the sprite's status is cleared to 0, meaning that it will no longer exist. Exactly what Yoshi does when swallowing sprites. Then the sprite's ID is compared to hex 21, which is the ID of the moving coin. It turns out that the moving coin is handled completely separately from any of the other power-ups. This is a hard-coded check that splits off the code of the moving coin from that of the more general power-up code. It is for this reason that the moving coin isn't really treated as a power-up, since it never runs the code we're interested in, which is coming up. Instead, it runs its own routine, which is responsible for displaying the sparkles that appear after collecting one, as well as calculating how many points and lives Mario gets from collecting the silver variant of the coin, which only appears after hitting a silver P-switch. We're not too interested in what happens there, so we'll skip forward to the more general power-up code. First, an aside. When a power-up is collected, two things happen. One, some sprite is possibly put into the item box, and two, something happens to Mario. For example, if Mario collects a super mushroom, nothing goes into the item box, and Mario becomes big. Then, if he collects a fire flower, a super mushroom goes into the item box, and Mario becomes fiery. However, this isn't quite so straightforward. If Mario is fiery and he collects a super mushroom goes into the item box, and nothing happens to Mario. This is different from what happened the first time, where nothing went into the item box and Mario growing. This is because these two events are not only dependent on what sprite Mario touched, but also his current power-up status. So there should be 4 different possibilities for what happens when Mario touches a super mushroom. One for if he is small, one for if he is big, one for if he is fiery, and one for if he has a cape. For some of these power-ups, all of the possibilities are identical, like the Starman. No matter what Mario's power-up status is, the item box item doesn't change, and Mario gains invincibility. However, the game breaks up every sprite into its 4 possibilities, because it is just easier to treat all sprites the same instead of making even more special cases. This is the first thing that the general power-up code does. When this code is called, the accumulator A contains the ID of the sprite that was collected. Then the constant hex 74 is subtracted from that. This gives us what that sprite's item box number is, -1. So the super mushroom would be 0, the fire flower would be 1, and so on. Let's look at these numbers in binary. It will be useful for what's coming up. Whichever number we end up with is shifted left twice, and logically ORed with Mario's current power-up status. This value is 0 if Mario is small, 1 if he is big, 2 if he has a cape, and 3 if he's fiery. These power-up status values are all less than 4, so they only take up 2 bits. That's why the item box number was shifted left 2 bits, so that the lower 2 bits here could hold the power-up status. What this does is creates an index for every kind of combination of sprite item box number and Mario power-up status. The upper 6 bits of this number denote which power-up was collected, and the lower 2 bits denote what power-up state Mario was in when he collected this power-up. For example, 0 represents touching a super mushroom as small Mario, 1 represents touching a super mushroom as big Mario, while 4, or 100 in binary, represents touching a fire flower as small Mario, and so on. 5 different sprites, mushroom, flower, star, feather, 1-up, times 4 different power-up states, small, big, cape, fire, equals 20 different possible combinations. All 20 options are assigned 2 numbers, one for what sprite to put in the item box, and one for what action to take to transform Mario. Here is the table for the item box items. These numbers represent the sprite's item box number, so 1 is super mushroom, 2 is a fire flower, and 4 is a cape feather. You'll notice that there are no 3s or 5s here, and that is because there is no way to legitimately get a Starman or a 1-up mushroom in the reserve item box. Maybe at one point in the game's development it was possible, but it isn't anymore. There are also a bunch of 0s in this table, which just corresponds to not changing what is already in the item box. If it is empty to start, don't put anything in there, and if there's already some item, leave it be. And here is the second table for what action to take on Mario. There are 6 different possible actions. Make Mario grow from small to big, give Mario fire powers, give Mario a cape, give Mario invincibility, give Mario a 1-up, and also just no action at all. Confusingly though, they are arranged in this order, so it's actually 1 that means do nothing here. With this point of view of everything, you can easily see that Starmen and 1-up mushrooms seem kind of shoehorned into this system, because they always perform the same action, either granting invincibility or giving an extra life, and never put anything into the item box. You can also easily see what would happen if Fire Mario were to collect a Cape Feather. The Cape Feather has sprite ID hex 77, so we subtract hex 74 and shift left twice to get hex C. Fire Mario corresponds to power-up state 3, so we logically OR hex C with 3 to get hex F. This would be the 0-based index into both of these tables, which means we would look at the 16th entry of each one. We see that a Fire Flower would be put into the item box, and that Mario would be given a cape, which is exactly what we would expect in this case. Okay, back to the code. So we subtract hex 74 from the sprite ID, shift left twice, or with Mario's power-up state, and then transfer that result into the Y register so that we can use it as an index into those tables. The first load here gets the item to put in the item box. It checks if the result is 0. Remember that 0 means to not touch the item box contents at all. If that is the case, the game will branch forward a bit and skip the next instructions. Otherwise, it puts that value into the memory address that determines which item is actually in the box. Then, a sound effect is played to tell the player that something just got saved into their item reserve. The next thing that happens is loading in the number that corresponds to what action to take. Then, a special function is called. This function requires that a list of pointers follows it. And indeed, 6 pointers to the 6 different routines that correspond to the 6 different actions follow this JSL. There's the Make Mario Bigger, Do Nothing, which just skips straight ahead to playing a sound effect, Give Invincibility, Give Cape, Give Fire, and Give 1-up routines. This function will jump to one of these pointers depending on what value is in the accumulator, which in our case is the value we grabbed from the second table. Then, once whichever routine we picked returns, it just returns to the caller of this power-up routine altogether, completing the processing of the power-up interaction. So that explains the entire grabbing a power-up situation, but where are the Trojan Chucks? And where are the clouds? Well, that's the thing, they aren't in this at all. They were never intended to be a power-up, so aren't taken into account by this algorithm at all. Since the routine gets an unintended input, it produces an unintended output. But what part goes wrong specifically? Well, look at the 2 tables we made. They are both 20 entries long, because we knew that there were 20 different combinations of power-up touched and Mario power-up status. Therefore, the index we calculate can never be larger than the size of our table, right? Well, when the power-up we touch is not any of the 5 intended power-ups, this index can definitely be greater than 20, and therefore the tables can get indexed way out of bounds. This is because there is no bounds check in the code. If everything works correctly, you wouldn't even need one, since you know the scope of your inputs. The fact that we can get a power-up that has a sprite ID of hex 91 or higher means we can get an index of 120 or higher, way larger than the 20 we expected. Let's see how wrong this can go. Suppose for a moment that sprite hex 79 was a power-up. It's not, but it makes this example easier to follow. And suppose Mario had firepower. First we subtract hex 74 from 79 to get 5, and shift that left twice to get hex 14. Fireflower Mario has power-up ID 3, so we logically OR that in to get hex 17, or 23 in decimal, so we'll be looking for the 24th entry. This is greater than 20, the size of our tables, so what ends up happening here? Like I said, there's no bounds checking, and there's no way the CPU knows that this is out of bounds for this table. All it sees is a read instruction. The CPU will just continue past the end of this table and read whatever byte lies behind it. In this case, the second table is directly after the first, so the first value, which should correspond to what item to put in the item box, will end up reading from the second table instead, specifically its fourth entry. Now this happens to be 1, which means the sprite with item box number 1 will be put in reserve, a super mushroom. This just happens to be one of the kinds of values we expect, so this isn't too crazy. But let's look at what happens with the second table. The second table will also get indexed out of bounds, and so we need to know what lies after this table in memory. I didn't lay out this code on screen like this for no reason, since this power-up function is what comes right after the table. Now, how in the world is the CPU going to read data from code? Essentially, the instructions here are just human-readable versions of the machine code that actually lives in the game's memory. Each kind of instruction corresponds to a different byte, and here's what this function looks like under the hood. The SEC instruction is encoded as hex 38, the SBC as hex E974, and the ASLs as hex 0A, etc., etc. Again, the CPU will just continue past the end of the table, so we have to read the fourth byte of this assembly code. This means that this hex A byte will be read. This corresponds to what action to take and which of these routines to call down here. Now we have a bigger problem. There's only 6 pointers here, and somehow we're supposed to jump to the 11th one. Just like how the earlier tables got indexed out of bounds, this list of pointers gets indexed out of bounds as well. Each pointer is 16 bits, or 2 bytes, so we have to find the 11th pair of bytes. There is more code after this list of pointers, but instead of treating those bytes as code, we'll be treating them as 16-bit pointers. If we march far enough down, eventually we find the pointer we are looking for, which looks to be hex 1496. Now, the important thing to know right now is that this pointer almost certainly doesn't point to any meaningful game code. In this case, it actually points to RAM, but for any given glitched power-up, this pointer can really be anything. This is because the pointer is really just unrelated game code being treated as a pointer, so it's not expected to make any sense at all. If the pointer happens to point to game code, then some weird glitchy stuff may happen, but the game will continue chugging along. If the pointer points to something other than game code, it is more likely to just crash the game and lock up forever. Like in this case, if the pointer points to RAM, then really anything can happen, because this also depends on the state of memory and exactly what values are in those RAM addresses at the time this function is called. And then there's a fourth case that we'll get to in a bit. Just a quick side note. In this case, it was the power-up that was the errant input, while Mario still had a valid power-up status. There are glitches in the game that can change Mario's power-up status to be something other than the intended range of 0, 1, 2, and 3. This means that even the intended power-ups can cause glitches if Mario's power-up status is glitched. For example, if Mario has a power-up status of 8 and he touches a mushroom, he will gain invincibility instead. This is because Mario's power-up status now exceeds the 2 bits that were allotted to it in the combination index, and this is now treated the same as if he was small and touched a Starman. As you can imagine, there are many different combinations of power-up statuses and power-ups when you include the unintended power-ups like the invisible solid block and all 8 charge and chuck variants. In fact, this increases the number of possibilities from 20 to 56. If you include the possibility of glitched Mario power-up states, you can increase that all the way to the maximum of 256. But what we're interested in is what happens in the 11 exit speedrun. In this case, we get Yoshi to eat an ordinary charge and chuck while Mario is small. So let's run through the code and see what happens. The charge and chuck has sprite ID hex 91, so we subtract hex 74 to get hex 1D. Shift that left twice, which is the same as multiplying by 4 if you haven't noticed, to get hex 74. Well, that's a coincidence. Mario's power-up status of small is just 0, so logically ORing that in doesn't change anything. This makes our index into our two tables hex 74, or decimal 116, which means we'll need to find the 117th entries. Yeah, that's overflowing by quite a bit. No worries, that just means we have to march quite a ways down past our tables into all of this code to find the values we need. The first table reads a value of hex 14, which is the item box number of the sprite that goes into the item box, Lakitu's Cloud. The second table reads a value of hex A9. This means we have to look for the 170th pointer in that list. So now we have to go way, way down. Looks like our pointer is going to end up being hex 4A13. So where does that end up? Is this some game code? Is it RAM or what? Oh boy. Part 2. Magic Open Bus Ride. Some parts of the memory space are not allocated to anything, like the game's ROM, work RAM, etc. These locations are referred to as open bus, since the data bus is left open. In other words, no memory chip is controlling it. I have done an entire video on why open bus exists from the hardware's point of view, so please check out the card that pops up here, or a link in the video description if you want to learn more about that. However, in this video, I'll explain what open bus means from the software's perspective, since it can be very weird. Let's imagine the CPU is planet Earth, and the memory space is outer space. There are a few planets out there that correspond to each of the different memory chips that might be allocated some of that memory space. Say, work RAM, cartridge ROM, cartridge static RAM, and so on. In order for the CPU to read or write data from or to any of these chips, it needs a data bus to receive and send information, as well as an address bus to communicate which memory address it is interested in. We'll represent that with some satellite stations or something. To read data from memory, the CPU puts the memory address it wants to read from on the address bus. Imagine this just blasts signals out into all of space in this analogy. Then it's up to the memory chips to respond to that memory address, but it will only do so if that address is within the allocated space for that chip. So if the CPU wants to read from, say, hex 7E1234, then the work RAM planet will respond with the data at that memory location, since hex 7E1234 is allocated to work RAM. This data ends up in the data bus, and ultimately in the memory data register, or MDR. Then, if the CPU wants to read from ROM at hex 00ABCD, then the cartridge ROM planet will respond with the data at that memory location, and it will end up in the MDR. If the CPU wants to write some byte to some memory address, then it puts the memory address in question in the address bus and the data to write in the MDR and blast signals out into space. Then it's up to the specific memory chip that is allocated to the memory region that includes that address to pick up on that information and store that data in itself. Open bus is when no memory chip planet responds to a CPU's read or write signal, because there is nothing allocated to that address. For a write operation, this essentially means nothing happens. That data byte still gets put onto the MDR, but there's no one to accept the data, so it doesn't actually get written anywhere. For a read operation, though, this is where things get unintuitive. The CPU will put a memory address like hex 014A13 on the address bus and blast that out into space, but no one will respond. What gets read by the CPU in the end? It's not 0, and it's not all 1s either, but it is deterministic. The data read is whatever was in the MDR last. The memory data register never gets reset at any point. It just continues to hold the last value it had until it gets overwritten by something else. So in this case, the CPU will read the value hex 53, since that is what the MDR holds right now, only because of the previous write operation. As long as the CPU continues to try to read memory addresses that aren't allocated to anything, it will repeatedly read the stale value in the MDR over and over again. If it just writes one single different value, even if it doesn't end up anywhere useful, the MDR value will change, and then more successive reads will return that new value over and over. Okay, so that's what happens when the CPU tries to read or write to a memory address that isn't mapped to anything. But in our case, we are jumping execution to open bus. We are telling the CPU that we want to execute the code that is at the memory location hex 014A13 when there is nothing there at all. We have to go a level deeper. So not only is the MDR used for reads and writes from instructions, but it is used for the reads when fetching instructions to execute. Normally, we have a chunk of code somewhere in the game's ROM that we are executing. Remember, this code is just a representation of the machine code that lies somewhere in memory. Those bytes have to be fetched by the CPU, that is, read from memory, in order for the CPU to know what instruction it needs to execute next. All of the bytes in this machine code go through the MDR just like the data from before. Let's take, for example, this bit of code from before. This code is located in the Japanese version of the game at ROM address hex 01C544. So first, to execute the first instruction, the CPU will put this address on the address bus and blast signals out into space. The cartridge ROM chip will respond to that and return the value hex 38, which is the underlying machine code for the instruction SEC. This lands in the MDR where the CPU can read it and then do whatever it needs to implement the SEC instruction. Then it will increment its program counter by 1 and put that onto the address bus, hex 01C545. The cartridge ROM chip responds with hex E9, setting the MDR to E9, which the CPU sees and recognizes as a subtract instruction. But it also recognizes that this subtract instruction requires an operand, so it will increment the program counter, put that onto the address bus, and read another byte. The ROM will respond with hex 74, setting the MDR to 74, and then the CPU can do what it needs to do to subtract this from the accumulator. This means that just executing code will update the MDR even if you aren't executing any load or store instructions. The MDR will briefly hold every single opcode and operand of every instruction that gets executed. Let's look at another example. Suppose the program counter is hex 014A13, and the MDR somehow had the value hex AF in it. First, the CPU will put this address on the address bus and read the opcode of this instruction. Nothing responds to its signal, but the MDR had hex AF, so the CPU starts to execute the instruction with the opcode of hex AF, which is a load instruction. This instruction also requires 3 operands for a 24-bit address to load from. The CPU will attempt to read the next 3 bytes from memory, which are all also open bus, so they all return hex AF as well. So the instruction realized ends up being LDA hex AF AF AF. The CPU will now attempt to read the data at that memory address as part of the load instruction, so that goes onto the address bus. This is actually a valid ROM address, so let's say the byte in ROM at that location was hex 5C. This updates the MDR with hex 5C, and that gets put into the accumulator, implementing the LDA instruction. Now the CPU wants to execute the next instruction at hex 014A17. It tries to fetch the opcode, but again, nothing responds since we are still executing from open bus. This time though, the MDR is hex 5C, so the instruction with opcode hex 5C will be executed, a JMP instruction. This jump instruction requires 2 more bytes for the memory address to jump to, so 2 more hex 5Cs get read from the MDR. The instruction ends up being JMP hex 5C5C. This updates the CPU's program counter to hex 015C5C, which is open bus still. The CPU tries to execute the instruction here next, but nothing responds, so it gets hex 5C again from the MDR. And here you can see that we'll be stuck in an infinite loop forever. The JMP instruction never modifies the MDR, since it's not a read nor write instruction, and the program counter will keep getting reset back to 0, 1, 5C, 5C over and over again, meaning it will never leave open bus. Let's walk through what happens when Yoshi eats that charge and chuck. We have to start at the instruction that is responsible for jumping execution into open bus in the first place. Looking back at our code, I guess I do have to look into this special function after all. You can take a look at it and try to figure out what's going on if you'd like, but the only important thing for this video is that it copies the pointer in the list that we want to jump to into work RAM at address 0. The low byte goes into address 0, and the high byte goes into address 1. The bank byte, which is the upper 8 bits of the 24-bit program counter, is just copied from whatever the bank byte was before this function call. We were executing from hex 01 C5 5C, so the bank byte is 1 in this case. It gets put into work RAM address 2. The last instruction in this function is this JML indirectly at address 0. What this instruction does is reads the 3 bytes at the specified address, in this case 0, and forms a 24-bit pointer out of them and jumps execution to that address. In our case, this pointer is hex 014A13. Address 0 has hex 13, address 1 has hex 4A, and address 2 has 01. Now, the MDR will change with each individual read operation within the instruction, so we have to see what happens when this instruction gets executed. First, the opcode byte of the JML is read, which is hex DC. The CPU will realize this is a JML instruction and will proceed to read the next 2 bytes as operands. These are both 0. Now the CPU knows to read the 3 bytes at address 0 in memory to get the jump target location. These are read in the order of low byte, high byte, bank byte. So first, address 0 is read, and the MDR becomes hex 13. Then address 1 is read, and the MDR becomes hex 4A. And finally, address 2 is read, and the MDR becomes 1. The CPU then sets its program counter to this 24-bit address it just grabbed, so execution jumps to hex 014A13. This is open bus as we have already noticed, but now we know that the MDR is 1 when we get to this point. So now the CPU is trying to execute the code at memory address 014A13. Of course, there's nothing allocated to that memory address, so when the CPU tries to fetch instructions, it just gets back the stale value in the MDR instead. First, it tries to fetch the first opcode, which ends up being the 1 in the MDR. This is a logical OR instruction and requires 1 operand. The operand will, of course, also be 1, so the instruction becomes ORA indirectly at address 1 indexed with X. So this is also an instruction with an indirect addressing mode, just like the jump we saw earlier. The difference here is that we have to add the value of X to our operand of 1 before fetching another address. At this point in time, X still holds the sprite slot that the power-up we collected is in. During this particular setup of the cloud glitch, the charge and chuck ends up in slot 9. This means that X equals 9 at this point, and means that our indirect address becomes 1 plus 9, or hex A. Now these parentheses mean we only need to fetch a 16-bit address instead of a 24-bit address. The bank byte is just inferred from the current databank register value, which is 1. This means we have to grab the low byte of this address at memory location hex A, and the high byte at address hex B. These memory locations, really all memory locations from 0 to hex F, are used as common scratch RAM, which means they are used for all sorts of purposes, mainly as temporary backups of CPU registers when something requires handling more than 3 numbers at a time. In our case, it just so happens, at this point in time, these 2 bytes hold the upper 8 bits of Yoshi's current X and Y position within the level. If we look at a map of Yoshi's Island 2, you can see that when we are performing the item swap right here, Yoshi has a Y position of hex 100 something and an X position of about hex 800. It's actually important that Yoshi stays back from this ledge a little to the left, because we need his X position to be less than hex 800, specifically so that it is hex 700 something as we'll soon see. This means that address hex A and B hold the values 7 and 1 respectively. The CPU reads address A first and gets the value 7 back, which updates the MDR to 7. Then it reads address B and gets the value 1, which updates the MDR back to 1. Now the CPU can finally form a memory address out of these 2 bytes and perform one more read operation to complete this OR instruction. The address it forms is hex 010107. Memory address hex 010107 holds a value that is dependent on which sprite graphics are currently loaded in video memory. In Yoshi's Island 2, this value is always hex 17. So when the CPU reads this byte to perform the logical OR, it gets back hex 17, which means the MDR becomes hex 17. Time for the second instruction. This one is at hex 014A15. As per usual, the CPU tries to fetch an opcode byte but gets no response, so the MDR value of hex 17 is read. This is another logical OR instruction, but with a different addressing mode. It also has one operand, which is hex 17 again. So the instruction becomes ORA indirectly at address 17 indexed with Y. The brackets here indicate that it is another indirect address instruction. This time, we have to read 3 bytes from memory address hex 17 to form an address to read from. Memory address hex 17 for the low byte, hex 18 for the high byte, and hex 19 for the bank byte. Memory address hex 17 holds the status of the A, X, L, and R buttons. The upper 4 bits will be 1 if the A, X, L, or R button is being held down, or 0 if they are not being pressed. The lower 4 bits are just always 0. This is where the player actually has some input on what happens during the open bus execution. By changing which buttons are being pressed, this instruction will read a different byte in memory. This will in turn change the value that is read and change the MDR value. And this will then change what instruction gets executed next by the CPU. As you can guess, there are lots of possibilities here, especially if we end up reading values from work RAM, because a lot of these values we can control by doing something in the level beforehand. Is that foreshadowing? Anyway, we're already spending a lot of time on this code analysis, so I'll just cut to the chase and tell you that we want to be holding the buttons R, L, and X. That's where the name of this strategy comes from, the Rolex cloud. Rolex, RLX, get it? Holding down these 3 buttons means that the memory address hex 17 holds hex 70. The CPU reads this value, and so the MDR becomes hex 70. Memory location hex 18 is similar to 17, but this byte indicates which of these 4 buttons were actuated on this frame. If we relied on this byte to be anything other than 0, it would make this trick frame perfect, so let's not do that. If we don't press any new buttons on this exact frame, then the value read here will be 0. So the CPU reads 0, and the MDR becomes 0. Now memory location hex 19 is where Mario's power-up status is held, funny enough. In this case, Mario will always be small, so his power-up status will always be 0. The CPU reads 0 again, and the MDR stays 0. Now the CPU has the entire 24-bit address of hex 000070 to work with. This particular OR instruction requires the Y register to be added to this indirect address first, so let's do that. Remember our check power-up routine from ages ago? We used the Y register to hold the combination index of Mario's power-up status and the touched power-up's item box number. Well, Y still holds that value here, so we know that Y is still hex 74. The CPU adds hex 74 to 70 to get hex E4, and this is the effective address that will wrap up this logical OR instruction. Now, address hex E4 holds the lower 8 bits of the X position of the sprite in sprite slot 0. There currently isn't any sprite in slot 0. However, when a sprite despawns in this game, it essentially leaves all of its data from the last frame it existed in all of the relevant memory locations. It doesn't clear or reset anything. Which means that this memory address effectively holds the lower 8 bits of the X position the last sprite in slot 0 had before it despawned. Now, since sprites load in by taking the highest number slot available, slot 0 doesn't get used very often, since something will only spawn into that slot if all the other slots are full. Luckily, in Yoshi's Island 2, there is a giant group of Koopas at the start of the level which almost fill all of the slots. All we have to do is jump on one of them to pop them out of their shell, which spawns one more sprite and fills slot 0. We can control where this new sprite is horizontally on the screen by jumping on a specific Koopa's shell at a specific location. There are a handful of different X positions that will allow this item swap to work, but the quickest and most consistent one to hit is hex B5. All you have to do is jump on the next to last Koopa so that he flies off to the left, and he will end up at X position hex B5 most of the time. Then, when the CPU reads the address hex E4 to finish the logical OR instruction, it reads hex B5, which in turn updates the MDR to hex B5. Third instruction. I've explained 2 instructions in 9 minutes? That's good for an IPS of 0.0037? Anyway, the program counter is now hex 014A17. Still open bus, so the CPU fetches the opcode of hex B5, since that's what's in the MDR now. This is a load instruction, and it also has one operand. The instruction is simply LDA hex B5 index with X, and we know that X is already 9 since it hasn't been changed since the last time we used it. We add 9 to hex B5 and get hex BE, so we need to load the byte at address hex BE. This memory location holds the horizontal speed of the sprite that is in slot 8. Again, there's no sprite currently in slot 8, so we end up reading the horizontal speed of the sprite that was last in slot 8 right before it despawned. In this particular setup, this was this Koopa who was inadvertently killed when Yoshi grabbed his shell earlier. Sprites that are killed and flying off the screen are given a horizontal speed of 16, and in this case, the Koopa is flying off to the right, so specifically positive 16, or hex 10. So this is what gets read by the CPU at address hex BE, which means this is what the MDR gets updated to after this instruction. Now the fourth and final instruction, or more like instructions. The program counter is hex 014A19, and the CPU fetches the opcode of hex 10 from OpenBus. This is the instruction BPL, or branch if plus. A branch instruction will add its operand to the program counter if the branch condition is true, the operand being hex 10, of course. The value we are checking against is the last value loaded into the accumulator. This is the horizontal speed of the sprite from the last instruction. Its speed is always positive 16, so this branch will always be taken. This means the program counter increases by 2, the 2 bytes taken up by this branch instruction, and then by 16 more. This makes the program counter hex 014A2B. Now notice that the MDR was never modified during this instruction. This means that the same BPL instruction will be executed over and over and over and over again. However, unlike the jump instruction I used as an example earlier, this branching instruction is advancing the program counter forward by 18 each time it is executed. This means that eventually we will hit the end of the OpenBus memory region and run into a memory region that is allocated to the game's cartridge ROM. And so we do. After 767 BPLs are executed, the program counter finally hits hex 018007, which is a ROM address. But we're not safe yet because we still need to execute a return instruction, an RTS, before we can be sure that the game will not crash. ROM address hex 018007 doesn't hold code, but it holds a table of data instead. The first instruction executed here is actually partially data and partially code. This is the intended code for this area, but it's not what gets executed by the CPU. When the opcodes of instructions are treated as operands, and the operands are treated as opcodes, we say that the CPU is currently desynced. It's like if you were to mail a letter, but treat the zip code as the house number and vice versa. You are indeed mailing a letter, and you have the right information, it's just interpreted incorrectly. That's what's going on here. The CPU is executing code that is meant to be code, But it's all wrong because the program counter is desynced. All because it happened to land 1 byte before this subroutine starts, instead of directly on its entry point. Luckily though, desyncing will commonly fix itself after a few instructions, which allows the CPU to sync back up to the proper instruction alignment. And then finally, after all of that, we run into an RTS at address 018013. This allows the game to return from the routine that processes touching and collecting a power-up and allows it to continue handling other game logic with no issues. Part 3. There's glitches in my cloud. Okay, so real quick, what's up with this? This is clearly not Lakitu's cloud. Okay, when you release it with the select button it shows up fine, but why is it so glitchy while it's in the item box? It's because sprites are drawn completely differently while they're kept in reserve. When out in the level like normal, the code that is responsible for handling how a sprite behaves and interacts with the world is also responsible for drawing it onto the screen using the proper object tiles found in video RAM. However, when an item is in the item box, it is the code that is responsible for drawing the status bar that handles drawing the item inside the box. Therefore, a sprite can look different depending on whether it is inside or outside of the box. And as you could probably guess, the status bar only expects certain kinds of sprites to be in the item box. So again, if you give it an unintended input, you'll get an unintended output. The status bar only expects 4 different kinds of sprites in the item box: the Super Mushroom, the Fire Flower, the Starman, and the Cape Feather. The 1-up is not taken into account here, so it was likely never meant to go in the box at any point. The Starman does though, and in fact it even has a special case in the code. It's the only sprite that will animate while it's in the box. Other than that, these 4 sprites are assigned 2 bytes each, which correspond to which object tile from video RAM to use, and other properties such as its color and orientation. Here is what all of the object data from video RAM looks like. The Super Mushroom is assigned tile hex 24 and palette 4, the red palette. The Fire Flower has tile hex 26 and palette 5, the green palette. The Starman has tile hex 48 and palette 0, but that is actually overwritten by the special code I mentioned. It cycles between palettes 0, 1, and 2, which is actually different than what it normally uses, which is 0, 2, and 4. Probably a bug. And the Cape Feather has tile hex 0E and palette 2, the yellow palette. These properties are kept in their own tables, and what seems to be a recurring theme, they get indexed out of bounds. These tables are indexed via the sprite's item box number, so 1 for the mushroom, 2 for the fire flower, you know it. Remember, 0 means there is no item, so the status bar knows to leave the box empty. When you get a sprite with an item box number greater than 4, the tile number and palette to use are junk and can be anything really. For example, the 1-up has item box number 5. This results in the status bar drawing object tile hex 100 using palette 3, the blue palette, and flipped upside down. This may look like a blue Yoshi egg, but if you release it, you see that it's just a normal 1-up. Lakitu's cloud has item number hex 14. This results in the status bar drawing tile hex 1BF with palette 4, red, and flipped upside down. Notice that this object tile straddles the border here, so it wraps around and draws tiles from both sides. That's because this object is set to be a 16x16 object, so it consists of 4 8x8 tiles. These tiles being hex 1BF, 1B0, 1CF, and 1C0. Fun fact, the Virtual Console and Nintendo Switch Online releases of the game don't emulate the hardware correctly, and instead the tiles drawn end up being hex 1BF, 1C0, 1CF, and 1D0 instead. On the original Super NES hardware, there's no carry from the 4th bit into the 5th bit when determining the group of 8x8 tiles that together form a larger 16x16 object. Anyway, that's why the cloud, and really any other glitched item, looks the way it does. Additionally, any object that uses tile hex 100 or greater is part of the tileset-specific sprite graphics area. This means that the graphics will change depending on what level you're in. This is what the cloud looks like in Yoshi's Island 2, but it changes for each level. The tile number is always hex 1BF, but tile 1BF just looks different in each level, since levels only load in the graphics they need to display the certain set of sprites and graphics in that level, hence tile sets. Part 4. Cloudy with a Chance of Mechakoopas. So all of that was about obtaining the cloud, but what do you do with it? It turns out that we can use it to manipulate Bowser's actions. We can skip animations and make him drop Mechakoopas faster. But first you have to get the cloud to the final fight. Taking damage while Big Mario will automatically make any item in reserve drop down, so if you get hit, it's run over. If you'd like to learn more about the 11-exit speedrun, there's definitely more interesting techniques other than the cloud glitch, you should check out Bismuth's video on the 11-exit speedrun. Link is in the description. But as for now, let's skip forward to the final room in the game where Mario has to take down Bowser. Let's review how the Bowser fight even works for just a moment. Bowser has several different modes which make up the entirety of the fight. First, he descends from the sky, which I'll call the entrance mode. Then, he'll start flying around in the sky, dropping Mechakoopas and big steelies onto Mario below. Let's call that the attacking mode. When Bowser gets hit by 2 Mechakoopas, he'll fly away. That's the fly away mode. And then he'll drop a few waves of fireballs from the sky. That'll be fireball mode. And then he comes back to the battlefield, where Peach will throw Mario a super mushroom before the fight continues. We'll call this return mode. And then he goes back into attacking mode. There are 3 phases of the fight, so this loop is taken once more. Attack, fly away, drop fireballs, return, and attack again. In the final phase, after Bowser is hit 2 more times, he will go into defeated mode, and drop Peach from the clown car, and the game will end. Let's look at some of the various timers or counters that Bowser uses to control how long certain actions take. Upon the initiation of the fight, Bowser starts in entrance mode. His position is set to be way up above the screen, and his vertical speed is set to 1 pixel every 4 frames. Then when he reaches the target Y position of hex 10, a special memory address gets set to the value 164. Let's call this counter A. Counter A will count down once per frame, and when it hits 1, another counter, let's say A2, gets set to 36. That also counts down once per frame, and when it hits 0, Bowser will switch to attacking mode. In attack mode, another counter, we'll call it counter B, gets set to 120, and it ticks down once every 4 frames. While it's ticking down, Bowser will just fly around. His flight pattern depends on which phase of the fight you are on, but they all use the same counter. When counter B hits 0, the game will check if there are 2 Mechakoopas on screen. If there are 2 Mechakoopas on screen, the counter will stay at 0, but Bowser won't attack. There will never be more than 2 Mechakoopas present at one time. If there's only 1 or no Mechakoopas on screen, Bowser will pause for a bit and then attack with Mechakoopas or big steelies, again depending on the phase. After this attack, counter B is set to some value which also depends on the phase and what attack he will do next. Counter B will also get set to some value after he is hit with a Mechakoopa. Once Bowser is hit twice, he will switch to fly away mode. During fly away mode, Bowser ignores counter B and instead uses a different memory address, which we'll call counter C. Counter C is set to 0 at the start of fly away mode. This tells the game that Bowser should start flying away from the screen and appear to shrink. Once he's as far away as he'll get, the game increments this counter to 1 so that it knows to make Bowser start flying towards the screen and appear to grow. Then, once he's as close as he'll get, counter C is incremented 1 more time. The game checks if counter C is equal to 2 to determine if fly away mode has completed. If it has, it will switch over to fireball mode. Fireball mode is fairly simple. Counter B makes a return and is set to 128 at the start of this mode. Counter C is ignored. In fact, counter C is only used for flyaway mode and nothing else. Counter B again is decremented once every 4 frames, and once the counter hits 96, the game will attempt to spawn a fireball every 32 frames. However, there can only ever be 6 fireballs on screen at once. The fact that there are 2 phases of fireballs wasn't directly programmed at all, it's just a side effect of this limitation. Once the first few fireballs start to despawn, more fireballs can appear again. However, the timer that controls when the fireballs spawn is not correlated with counter B at all. And once counter B hits 0, Bowser goes into return mode and reappears on the screen. This is why the number of fireballs that drop is not always consistent. During return mode, Bowser uses counter A again to control how long it takes him to fly back into a position. It gets set to 255 and counts down once per frame. Once it hits 0, Bowser goes back into attack mode. And then finally, after you hit Bowser for the 6th time, he goes into defeated mode. He flies either up or down at 1 pixel every 2 frames to make his Y position hex 10 again, and then counter A is set to 96. It counts down once per frame again, and when it hits 0, Bowser turns upside down. Then counter A2 gets set to 32, counting down as usual, and when that one finally hits 0, Bowser releases Peach, ending the run. So to review, entrance mode uses Bowser's position and counters A and A2. Those are also used by return mode and defeated mode. Attack mode and fireball mode use counter B for timing purposes, and counter C is used only by flyaway mode. The reason for these distinctions is that Lakitu's Cloud can help us manipulate counters B and C. Counters A and A2 are unfortunately out of our reach. This means that we can use the Cloud to speed up the attack, flyaway, and fireball modes by a significant amount. Counter B is located at work RAM address hex 14B0. Counter C is located at address hex 14B2. And for completeness, counter A is located at address hex 1549, and counter A2 at address 1555. But again, we can't do anything with those ones. Why does Lakitu's Cloud use the same memory locations as Bowser? Well, the entire memory region from hex 14B0 to hex 14C7 is kind of a mess and is used by a handful of things in the game. This includes Bowser and Lakitu's Cloud, but also the brown swinging platform and Iggy and Larry's rotating platform. Sharing memory like this is completely fine as long as all of the entities that use the memory are mutually exclusive and never appear at the same time, which, under normal circumstances, this is the case. Bowser, Iggy, and Larry are all bosses that only feature them and nothing else. There should never be a cloud or a swinging platform in a boss battle, and likewise there should never be any bosses in a normal level that has a Lakitu or a swinging platform. The only close call here is the brown swinging platform and the cloud. However, remember what I said about tile sets? Lakitu and this platform are in different tile sets, so they would never be able to appear correctly in the same level anyway. So it wasn't really a mistake to have all these sprites share the same memory addresses. But here's the thing, the cloud seems out of place with all of these other sprites. All of the others, Bowser, Iggy, Larry, and that platform, all rotate in one way or another. The cloud doesn't rotate, so what does it need this extra memory for? Let's look at the code. I know this looks like a lot, but most of it isn't that super important. Remember how I mentioned the scratch RAM before? The memory from address 0 to hex F? It turns out that this routine that is responsible for drawing the cloud to the screen uses up all 16 of those bytes. So the X and Y position of the cloud relative to the screen had to be copied to yet another temporary memory location to keep track of it. There are a lot of viable options for temporary buffers like this, and whoever wrote this code decided to use the memory used by Bowser and company. We can analyze this routine to see where it uses all 16 of the scratch memory bytes. Just for some context, this routine draws 4 16x16 objects and 1 8x8 object by calculating X and Y positions, as well as the tile numbers and attributes, and copying it all into the object attribute memory buffer. The cloud is made up of 4 individual cloud objects, 2 with lower priority and 2 with higher priority. And then a cute little smiley face is the 8x8 object on top of all of those. First, This helper function calculates a sprite's position relative to the screen and puts the x and y coordinates in memory addresses 0 and 1. So let's mark that down. Then, addresses hex C, D, E, and F hold 4 indices into the OAM buffer. These determine where in the buffer all of the cloud data will go. This creates a 4-byte long table with base address hex C. Here we can see that the X and Y positions of the cloud sprite are copied into the extra temporary memory locations at hex 14B0 and 14B2. Then the current animation frame of the cloud is stored into address 2, since the cloud has 4 different animation frames. Now we have this big loop that runs once for each of the 4 individual cloud objects. Each of those objects has a separate offset from the cloud's overall position. This loop reads those offsets and adds the base offset that is the cloud's position and writes the appropriate data into the appropriate locations into the OAM buffer. Now down here we see another helper function. This function essentially checks to make sure that the sprite is actually within the bounds of the screen and hides it if it is not. This way, if a sprite goes off the side of the screen, it won't wrap around and reappear on the other side. This helper function uses all of the scratch RAM addresses from 0 to hex B. These memory locations are set to various things, such as the sprite's X and Y positions in the level, the X and Y position of the individual objects that make up the sprite relative to the screen, the size of the objects, and the number of objects that make up the entire sprite. Funnily enough, addresses 6 and 7 get set to the cloud's overall X and Y position relative to the screen, which is exactly the values copied to the extra temporary memory locations. After calling these helper functions, though, both the X and Y position are needed one more time to calculate where to place the smiley face. So yes, all 16 scratch RAM values are used in this routine. However, the position of the cloud on the screen is always available somewhere. It's located in addresses 0 and 1 at first, and then it is found in addresses 6 and 7 after this helper function is called. Which means these instructions at the end could just use address 6 and 7, and these here in the middle could just use address 0 and 1. So it wasn't even necessary to back up the values to another temporary buffer. What was likely the case was that the developer who wrote this routine knew that this helper function clobbered the first 12 bytes in memory, but didn't know or didn't want to rely on how it manipulated that memory. It's possible that at some point in development, this helper function didn't leave the position ready to use when it returns. Even if we couldn't rely on the result of this function, it would still be possible to prepare the cloud's OAM data without needing the extra memory buffer. If you look carefully, you'll see that this routine doesn't use all 16 bytes of scratch RAM all at the same time. Addresses 0 through hex B aren't overwritten by the helper function until near the end, and this loop is done using addresses hex C through F, as well as addresses 2 and 3 once it falls through. This means that at this particular point in the code, they could have transferred the X and Y positions from addresses 0 and 1 to somewhere like addresses hex C and D and been just fine. In fact, there's no reason why we have to draw the smiley face last. If we draw the smiley face tile to the OAM buffer before we call the second helper function, then we don't need to move the X and Y position from addresses 0 and 1 at all. So I suppose that means this entire conflict between Bowser and Lakitu's cloud could have been avoided with better memory management. However, that's just not how the game was programmed. To the casual player, this makes no difference at all. But to a speedrunner trying to find the absolute fastest way to complete the game, it's just another quicker and more challenging technique. Finally, let's look at what you actually need to do with the cloud in order to manipulate Bowser's actions. Remember, counter B was used in attack mode and fireball mode. This is the memory address that is used by the cloud's X position on the screen. Bowser starts an attack and transitions from fireball mode to return mode when counter B hits 0. This means we can make these actions occur quicker by just making the X position of the cloud 0. In fact, as long as the cloud is not at X position 0, Bowser will never attack and fireballs will forever continue raining from the sky. X position 0 corresponds to the very left side of the screen. So all you need to do is move the cloud to the very left side of the room. Oh, that didn't work. So there is a small buffer zone on either end of the room that prevents Mario from touching the very edge of the screen, and this stops the cloud at X position 8. In order to move the cloud these 8 more pixels to the left, you have to kind of toss the cloud off the edge of the screen. Not so far to send it all the way off the screen, but just enough to hit X position 0, and close enough that it snaps back to Mario when he lands in it again. That's all there is to it. In order to force Bowser to attack, instead of having to wait around, just do this jumping maneuver with the cloud. Now, flyaway mode is different because it uses counter C instead of counter B. This is the memory address that is used by the cloud's Y position on the screen. Bowser will transition from flyaway mode to fireball mode if this value is exactly 2. A Y position of 0 corresponds to the very top of the screen, so 2 is just a little below that. So in order to instantly go from flyaway mode to fireball mode, you just have to fly up to the top of the screen. As soon as you get near it, the fireballs will start to come down, so you better watch out so you don't get hit. In fact, if you do the jump maneuver with the cloud at the left side of the room, while being up near the top of the screen, you can get the cloud at Y position 2 and X position 0 at the same time. This will skip flyaway mode and fireball mode at the same time, saving precious time. Using these strategies, all it takes is 8 really precise timed cloud jumps in order to skip as much of Bowser's animations as possible, which is exactly what you see most runners of 11 Exit of Super Mario World doing. Thank you so much for watching through this entire video. This channel is supported by viewers and contributors through Patreon. I would be sincerely grateful if you considered pledging even a small bit per month if you were able. Patreon memberships account for about 3/4 of my income, and every little bit helps. As thanks, you get early access to videos with no ads, no matter how much you pledge, and with a higher pledge you can even get your icon rolling around here, as well as behind-the-scenes content. Also, if you haven't seen already, I've made a co-host account and post little articles about smaller topics weekly. Feel free to check it out and give the account a follow. It's at cohost.org/rgmechx. There's also a link in the description. And again, thanks for watching.